Good afternoon, morning, all the above. So, what are we doing today? We are going to be working on pH and pOH and just calculating concentrations depending on the information that's provided to us. So, in this particular set, we're going to, this is POD 27, and we're going to be filling in the blanks given the information. So now one of the things that you need to do is make sure you know the equations that are important for calculating the different variables. So pH is equal to the negative log of the hydrogen concentration. If you want to go backwards and do the anti-log and you want to figure out the concentration of hydrogen ions, you need to do 10 to the negative pH. And the same thing is used for the pOH and the OH. Now, the one other equation we can have here, P14 is equal to the pH plus the pOH. This is based off the dissociation constant for water at 25 degrees Celsius. So now let's look at this problem we got here. So I'm not going to work all these, but I'll work 3 or 4 of them at least. So the first one is we're going to have a pH of 8.5. So we can do a couple of things. We can go ahead and calculate the hydrogen concentration. Let's just do that and get it out of the way. So to get the hydrogen concentration, we're just going to do 10 to the negative 8.5, and that gives me 3.2 times 10 to the minus 9. Now, if we want the pOH, we're going to use the last equation here, 14 is equal to pH. So we're just going to subtract the pH from 14. And what that gives us is 5.5 for the pOH. Now, the OH, again, is you're just going to go backwards to do the anti-log of the pOH. So 10 to the negative 5.5 gives me 3.2 times 10 to the minus 6. Now, the last column there is asking if you can determine if it's acidic, basic, or neutral. We can, as long as we know the pH. So remember, the scale goes from 14 to 0, 7 being neutral. If you're between 0 and 7, you're acidic. And if you're between 7 and 14, you're basic. So looking at pH here, 8.5, that is between the basic range, so that is a basic solution. Now we're going to go ahead and skip on down to the third row where it gives you the hydrogen concentration is 7.58 times 10 to the minus 3. You're going to calculate the pH, so we're going to use the first equation here. So we're going to take the negative log of this concentration. So negative log of 7.58 times 10 to the minus 3 gives me 2.12. Now, if you want the pOH, we subtract that from 14, and we have 11.88. To calculate the hydroxide, we do the anti-log of the pOH, so we do 10 to the negative 11.88. That gives me 1.3 times 10 to the negative 12. And this is molar, so concentration units are molar, just so you know. And last column is acidic, basic, or neutral. It falls between 0 and 7, so that is considered to be an acidic solution. All right, so let's do one more. Let's do the next column down, which would be column 4, or row 4. And in this particular row, they give you the hydroxide concentration. So all we're going to do is go backwards. We're going to calculate the pOH. To do this, we're going to take negative log of the 2.99 times 10 to the minus 14. And that gives me a pOH of 13.52. And then we're going to do 14 minus that to give us our pH, which is 0.48. And the last thing we do is calculate the hydrogen concentration. So we need to do the anti-log of that, so 10 to the negative 0.48, and that gives me a concentration of 0.33 molar. Now the final column there is acidic, basic, or neutral. Well, it's definitely much lower than 7, so that's acidic. This would be more considered a superacid almost, because it's really close to 0, and the higher concentration of the hydrogen concentration you have, the more acidic that becomes. So that's just a quick introduction and explanation of how we go about solving for pH, POH, hydrogen concentrations, and hydroxide concentrations. Now, we're going to use that information below. Now, the thing that you have to keep in mind is that what you want to do is understand the differences between strong acids and weak acids. That really makes a huge difference in how you go about solving for the pH or whatever the case might be. Now, in number 2, it says the pH of an aqueous solution of 0.015 molar HNO2 was measured to be 2.63. What is the value of Ka for HNO2? So, they give you the pH of the solution, which you can determine the hydrogen concentration from that. Now, HNO2 is a weak acid. HNO3 is a strong acid. So this is going to form an equilibrium. All right. And what we're going to do is we're going to write out the ice chart to help with establishing the different variables. And so now we know that this is 0.015. This is, well, this will be the 0 and 0 to begin with. This will be minus x, and then 0.015 minus x, and then this. All right, we've given the pH of 2.63, so the pH 2.63. Now, what we can do from this is the hydrogen concentration, and this is the hydrogen concentration at equilibrium. So that's what makes this a little bit of an easier problem, because it gives you the information that you need. Now, just like above, we want to figure out the hydrogen concentration, and so we need to do the anti-log of the pH. So 10 to the negative 2.63, that gives me a concentration of 0.00234 for our hydrogen concentration. Now, if you pay attention to the ice chart, the concentration of hydrogen, it really would be equal to X. So by us understanding and knowing this, the stoichiometry is 1 to 1 to 1, makes it a lot easier. So what we do know now is that this value that we calculated here is the value for X. So we know what X is equal to. So all we do then is we're going to write out our equilibrium expression, and then we'll do a little substitution here, and we can calculate our Ka value. So now the reason why you want to write the expression is to make sure that you factor in the stoichiometry from the balanced equation. The nice thing here is everything is 1 to 1 to 1, so we don't have any exponents that are greater than 1. It just simplifies it a little bit. So now we know that just based off of the equilibrium part here from the ice chart, that we have X and X on top divided by 0.015 minus X. Now that means that we're going to have 0.00234 times 0.00234 divided by 0.015 minus 0.00234. So we just input that into the calculator, and we go through the calculation. So I'm going to do that right now. 4 is here, and so 0.015 minus 0.4. So close that out. And what we end up with is a value of 4.33 times 10 to the negative 4 for our Ka. So the Ka for this acid is 4.33 times 10 to the negative 4. So what we can see here is we understand that you have to understand the fundamentals of these equations to calculate the pH, hydrogen concentration. And right here is a great example of how we are given the pH of the solution. We work backwards and we use that information to help us determine what X is. Once we determine X, we plug that into the equilibrium expression, and ultimately it helps us to determine the Ka for nitrous acid. So, all right, appreciate you guys watching. Thanks a lot.